Welcome back to video lesson 8, part 4. This is still optional, unless of course you miss class, in which case you should be watching this. Now when we left off on part 3, I was talking about how a chain of amino acids is often called a polypeptide, and that it's not referred to a protein until it actually hits its three-dimensional functional form. So as it's being made, the protein goes through several processes until it eventually gets to its mature form. So the first is what we call the primary form. As it's being made in your body. We abbreviate primary with a 1 followed by a degree. Okay? It is the simple linear, so basically a straight line, linear form of the chain of amino acids. So sometimes they'll represent it like this, with each little circle representing amino acid, or they might be a little more complex, and they'll give you that N, C, C, N, C, C, N, C, C form, with each NCC being an amino acid. So we gotta go back and fill in the details. Finish your amine group, hydrogen off the central carbon, remainder group, double bonded oxygen, double bonded oxygen, OH of the carboxyl group. So you might see something like that. And the way I recognize that as amino acid chain is I'm always looking for the NCC portion. Okay, so you're looking for this core repeating itself, representing a chain of amino acids. Of course, each individual amino acid would be that, and linking the individual amino acids together would be the peptide bond. Once you get that single chain of amino acids, they start interacting along the chain to form what's called the secondary structure. Okay, and there's two main forms of secondary structure. One's called a beta sheet. That's the symbol for beta. And this is kind of like old-fashioned computer paper, how it was always linked together. Okay, that's a beta sheet. And this is an alpha sheet, or sorry, an alpha helix, which we've talked about before for the structure of carbohydrates. If you remember, starch forms an alpha helix. It's kind of that spiral shape, kind of like a slinky. And why they form these shapes is basically hydrogen bonding. Think back to structure water when we talked about hydrogen bonds. Hydrogen bonding occurs between the carboxyl group which has an oxygen with a slight negative charge, and the amino group which has a hydrogen with a slight positive charge between amino acids along the chain. So basically, one amino acid here, it has its oxygen that's slightly negative, then interacting with another amino acid here which has its hydrogen that's slightly positive, and they're forming a hydrogen bond to hold that in the alpha helix shape. Alternatively, they'll interact and form hydrogen bonds, folding it into what's called a beta sheet or a beta pleated sheet. So that's the secondary structure. I don't know why I have an extra C in there, but we'll get rid of it. Then we have what comes after secondary. Do you guys know the word? It's tertiary. So our tertiary structure. In many proteins, this is as far as they get. Tertiary structure 3. It's for many proteins. It equals the final 3D shape and the functional form. And what causes the protein to further fold up are, so it folds according to interactions between the R groups. So based on whether they're polar, they might be on the outside of the protein because they like water, or non-polar, being hydrophobic, they'll be buried in the middle of the protein. Or the charges, positive and negative, will determine how it folds up. And that's generally the structure of a lot of proteins. But then there's still quite a few more who have a quaternary structure. Which we abbreviate with 4 followed by the degree sign. And what happens in a quaternary structure is you get 2 polypeptide chains, or more than 2 sometimes. 2 polypeptide chains come together to form the final 3D structure. And functional form. And a classic example of a protein that actually is made up of several polypeptide chains is something like hemoglobin, which helps transport oxygen and carbon dioxide in our blood. And now that we know a little bit more about the structure of proteins, we can look at the effect of temperature and pH on the structure and function of proteins. Indeed, that's one of the main reasons we need to maintain homeostasis. Because if you alter these things, you destroy or denature proteins. First is temperature. As we increase temperature, the atoms within a molecule tend to vibrate faster. Putting stress on the bonds. And if you apply enough heat, eventually the bonds will break. In particular, something like hydrogen bonds, they break quite easily. The bonds will break and destroy the protein's 3D structure, which in turn destroys its ability to function. This is why you need to be concerned if you get a fever that gets too much above about 38, 39 degrees, because above that you're going to risk starting to denature your proteins. And that's the fancy word. Denature is when you destroy both the three-dimensional structure and therefore its function. Then we look at pH. We were saying that the body has to maintain certain pHs in certain regions, and the proteins that are in that region function at those pHs, and if we mess with that, we mess with the protein and therefore their function. Just recall, acids are defined by their ability to release H plus ions. You have more H plus ions, you decrease pH. In contrast, bases are defined by their ability to release OH plus ions, OH negative ions, which will increase pH. And the impact of this is to mess with the electrical attractions that are occurring within proteins to hold them in their three-dimensional shape. So if you take something like, we'll draw a very simple protein. We'll go circles. Here's a protein. Has several amino acids in a row that have a negative R group. Negative, 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 negative. And then maybe it has some amino acids slightly different R groups. And then maybe it has a bunch of amino acids that have positive R groups, and these positive ones are going to fold back in an effort to bond with the negatives, and that's going to influence the three-dimensional structure of the protein. They're bonding because of their electrical attraction. But this isn't a permanent attraction. This can be transient. So they kind of open up and close a little bit over time. And if you suddenly add a whole bunch of positive or negative ions in here, they can get in the middle of it and interfere with these interactions. So you could have something like, if you added a bunch of acid, what's going to happen to this protein over time is it's going to denature. You're going to get all the negatives followed by your other R groups, followed by your amino acids with the positive R groups. Over time, those H plus ions from the acid are going to come in, and they're going to start interacting with the negative R groups and blocking out the interaction with the positive amino acids, and basically straighten out this protein. So they've replaced the interaction with the other amino acids and interfered.